Welcome to the deep dive. Today, we're venturing into something pretty massive, the Gaia mission, and its third early data release, EDR3.
Yeah, and we're not just talking about any data set here. This is billions of stars. It's a cosmic map unlike anything we've had before.
Absolutely. But the big question we're digging into, really, is how do scientists actually know this incredibly complex information is?
Well, right. How can they trust it?
Exactly. That's the core of it. You've got this satellite, Gaia, collecting unbelievable amounts of data, and ensuring its reliability is, frankly, a monumental task.
So our mission today, for you listening, is to explore those rigorous validation methods, sort of a behind-the-scenes peek.
It really is. You get to see the ingenuity involved in building confidence in this astronomical gold mine.
Goldmine is right. We're talking positions, distances, parallax, that clever trick,
Right, like your thumb shifting when you blink each eye. Same idea, but on a cosmic scale.
and proper motions, how stars move across the sky, plus brightness, radial velocities, all of it.
Yeah.
And to get a sense of the challenge, maybe think back to Hipparcos, the earlier mission.
Oh, yeah, Hipparcos. Revolutionary for its time. Didn't they have two separate teams analyze everything, just to be sure?
They did. FAST and NDAC. A great approach for validation, basically. Double-checking the entire process independently.
Smart. So why not just do that again for Gaia? Seems logical.
Well, the sheer amount of data from Gaia
Yeah.
and how intricate the processing is, just orders of magnitude beyond Hipparcos.
Oh, so having two teams do that would have been...
Unimaginably resource-intensive. Just not practical this time around.
Okay. So if you can't have two independent teams, how do you make sure everyone on the one massive team is, singing from the same hymn sheet? Over 400 people.
It was a huge logistical hurdle, yeah. Consistency is critical.
I can imagine. Like, everyone needs to use the exact same value for the mass of the sun.
Or the speed of light.
Yeah.
Or even pi, down to, 13 decimal places.
Yeah.
And then all the instrument details, the satellite spin rate, the exact size of the CCD pixels, how the filters respond to different wavelengths.
Sounds like a recipe for subtle errors creeping in everywhere if you're not careful.
Precisely. So the solution was elegant, really.
What did they do?
They set up a central parameter database. Think of it like the ultimate rule book,
Okay.
meticulously managed by Jos de Bruyne. It held all these fundamental constants and instrument parameters.
And everyone had to use that database.
Everyone. If you were processing Gaia data, you pulled your constants from that single source. It minimized the risk of teams using slightly different numbers.
That makes a lot of sense. A single source of truth. Okay, so they've got this foundation of consistent numbers. How do they actually start testing the results? The data itself.
Right, the validation. There are lots of ways, but one really neat example uses something relatively close to home.
Oh, yeah. What's that?
Solar system occultations.
Okay, when an asteroid passes in front of a star...
Exactly. Predicting those events used to be, well, a bit hit and miss before Gaia.
How hit and miss are we talking?
Predictions could easily be off by thousands of kilometers on the ground or hours in time. You might travel somewhere to see one and completely miss it.
Wow, okay, that's quite uncertain. So Gaia changed that.
Dramatically.
Huh.
With the super precise star positions and proper motions from EDR3, those predictions are now accurate down to within seconds.
Seconds. From hours and thousands of kilometers.
Seconds. It's a massive leap. It really shows you, in a very tangible way, just how accurate Gaia's basic measurements are. A powerful demonstration.
That really does hit home. Incredible. Now, you also mentioned something kind of counterintuitive sounding. Negative parallaxes.
Ah, yes. That often raises eyebrows.
It sounds like the star is, I don't know, behind us, which makes no sense.
Small chuckle. No, not literally behind us.
Yeah.
Remember, parallax measures that tiny angular shift as Earth orbits the sun. Smaller shift means farther away.
Right, the shift gets incredibly tiny for very distant stars.
Exactly. And any measurement, no matter how good, always has some uncertainty, some error bar associated with it.
Okay, standard errors. Got it.
So if a star is really, really far away, its true parallax is extremely close to zero. With the measurement uncertainty, sometimes the measured value might just happen to fall slightly below zero.
Ah, I see. So it's just a result of measurement noise around a very small true value.
Precisely. In fact, this is crucial if we didn't see any negative parallaxes in the data for these distant objects.
That would be weird.
It would be weird. You'd suggest we maybe don't understand our measurement errors correctly, or perhaps there's some bias pushing all the values up.
That's fascinating. So the presence of these negative numbers actually gives you confidence. It acts as a kind of sanity check on the error estimation.
Exactly. It's a built-in check.
Mm.
By looking at the distribution of these small and negative parallaxes and comparing it to models of our galaxy, we can test how well we've estimated those standard errors.
And someone figured this out before Gaia.
Yeah, Leonard Lindgren did pioneering work on this concept with the Hipparcos data back in the 90s. The same principle applies perfectly to Gaia.
Very clever. Okay, so that's one powerful test. What other specific checks did they run for EDR3? You mentioned a whole battery of them.
Oh, yes. Fabricius and the team detailed a huge range of validation tests, building on what was done for the earlier releases, DR1 and DR2.
What kinds of things?
Well, one fundamental thing is completeness.
Hmm.
Are all the stars we expect to see actually in the catalog?
Right, you can't analyze what Gaia didn't observe. Were there gaps?
There are practical limitations. Gaia can only observe so many stars at once due to things like onboard memory and how much data it can send back to Earth.
So in crowded areas.
Exactly. In really dense fields like near the galactic plane or in famous spots like Bade's Window, the catalog starts to become less complete for the fainter stars, roughly around magnitude 20, maybe magnitude 19 in those super crowded zones.
So for the very dimmest stars in the busiest parts of the sky, some might be missing in this release.
That's the gist, yes. They need more observation to refine processing for those, potentially coming in later releases.
What about slightly less chaotic places like globular clusters? Still dense, but maybe more manageable.
Good question. They actually used Hubble Space Telescope data to help calibrate completeness there.
Ah, comparing with Hubble, smart. What did they find?
Even in quite dense cluster regions, say, 100,000 stars per square degree they found, EDR3 is about 60% complete down to magnitude 19.
That's pretty good, surely.
It is. And even in the absolute densest cores, like 10 million stars per square degree, it's still over 20% complete for stars around magnitude 17. But there's a noticeable difference between the inner and outer parts.
Okay, so completeness varies. What about stars moving really fast across the sky? High proper motion stars.
Yeah, those are interesting. EDR3 includes quite a few, over 600 moving faster than 1 arcsecond per year, which is really zipping along.
Are they all nearby?
Generally, yes.
Yeah.
High proper motion usually implies closeness. But interestingly, when they compared EDR3 to other catalogs like Simbad,
Yep.
they found about 8% of known high proper motion stars weren't yet in EDR3.
Huh. Any idea why?
The expectation is they'll likely appear in future releases. It might be due to the specific observation pattern so far, or challenges in the processing for some specific cases. It's an evolving catalog.
Always getting better. Okay, what about stars that are in the catalog but don't have, say, a distance measurement?
Right. Stars without a full photometric solution, meaning no parallax or proper motion.
Why would that happen?
It affected about 1.5% of the brighter stars, those brighter than magnitude 19. Mostly due to the time window for EDR3, July 2014 to May 2017, wasn't long enough for a robust solution for every star.
Not enough observations yet.
Basically. And also, if a star has a very close neighbor, that can sometimes perturb the measurements or make the solution difficult.
Right, crowded neighborhoods again. So even for the stars with full solutions, are there still known sort of residual issues?
Yes, perfection is hard. There are still very subtle imprints left over from the way the satellite scans the sky, the scanning law. It creates slight inhomogeneities.
Okay, tiny patterns in the data.
Very tiny, but detectable. And they also found that some of the most significantly negative parallaxes, those outliers, could sometimes be traced to spurious solutions, perhaps influenced by nearby stars or areas where the sky coverage wasn't yet optimal.
So they're identifying the causes of these outliers. How do they check for systematic parallax errors across the whole sky, like a general offset?
They use things that should have essentially zero parallax. Distant quasars are perfect for this.
Because they're incredibly far away.
Exactly. Any measured parallax for a quasar is basically telling you about systematic error in Gaia itself at that point in the sky. So they use thousands of quasars to map out these large-scale variations.
Clever. Using the universe's distant beacons. What else?
They also look at stars in places where we have a good independent idea of their distance, like the Magellanic Clouds, nearby dwarf galaxies, or well-studied open star clusters.
Comparing Gaia's distances to those known distances.
Right. It helps check the overall zero point of Gaia's parallax scale and hunt for other systematic effects. It's like checking your ruler against known lengths.
Makes sense. And proper motions, how are those validated?
A key comparison is back to the Hipparcos catalog.
The predecessor vision again.
Yes. Comparing the proper motions between the two showed a very slight global rotation difference, but it was well within the known uncertainty of the Hipparcos reference frame itself.
So basically they agreed. within expectations.
Pretty much, yeah. It gives confidence that the overall system of how Gaia measures motion across the sky is solid.
You also mentioned a simulation tool, the Gaia Object Generator, GOG.
Ah, GOG. Yes, that's a really cool tool. It's essentially a sophisticated simulation of our Milky Way galaxy.
What does it simulate?
Based on our best understanding of galactic structure, star populations, and how stars move kinematics, it predicts what Gaia should observe if our models are right.
Okay, a theoretical Gaia observation.
Exactly. Then you compare the real EDR3 data to the GOG simulation output.
And how do they match up?
Broadly consistent, even down to very faint magnitudes. Which is great. It suggests both the data and our general understanding of the galaxy are, on the right track.
Does it reveal any issues?
Interestingly, some of the small remaining discrepancies might actually point towards limitations in the GOG model itself, rather than problems with the Gaia data.
Ah, so Gaia is so good it's actually testing our galaxy models.
In a way, yes. It's a feedback loop.
Fascinating. Okay, let's circle back to those parallaxes, specifically the negative ones. You mentioned deconvolving the parallax distribution. Sounds complex.
It is a bit technical, but the idea builds on what we discussed about negative parallaxes, revealing information about errors.
Using the negative tail.
Right. By carefully analyzing that negative tail of the distribution, you can mathematically estimate the true spread of parallaxes if there were no measurement errors.
Okay. Why do that?
It helps you figure out a few things. Are we underestimating our standard errors? Are there residual systematic biases we haven't accounted for? And how much might unresolved binary stars be contaminating the sample?
So it's digging deeper into the error properties. What did this method show for EDR3?
Good news, mostly. It confirmed that systematic error returns were generally smaller compared to the previous release, DR2.
Progress.
Definitely. The remaining issues seem mostly linked to either small calibration shortcomings or contamination from those non-single stars binaries or multiples treated as single.
And they could even quantify these remaining effects.
Yes, Lindgren and colleagues provisionally derived how the leftover parallax bias seems to depend on things like star brightness, color, and position on the sky. We're talking biases at the level of a few tens of microarseconds. Tiny, but important to characterize.
Amazing detail. You also mentioned binary stars themselves being useful for validation. How does that work?
Right. Resolved binaries, ones where Gaia sees two distinct stars, especially those with long orbital periods.
Why long periods?
Because if the period is long, the two stars are moving through space together. They should share the same distance and the same proper motion.
Ah, common proper motion pairs.
Exactly. So you find these pairs moving together, and then you check. Does Gaia give them the same parallax measurement?
And if it does?
It's another strong consistency check. Plus, by comparing the results for the brighter primary star and the fainter secondary, you can investigate subtle effects, like whether parallax measurement depends slightly on star brightness.
So they looked at lots of these pairs.
Yes, selected pairs across a range of brightnesses and checked the consistency of their parallaxes. It's like having thousands of little calibration pairs scattered across the sky.
Very thorough. Okay, we've covered position, motion, distance. What about the photometry? The brightness and color data?
Equally important, and it also went through a huge validation process, again detailed by Fabricius and the team.
Any big improvements there in EDR3?
One really significant one. Remember those subtle patterns linked to the scanning law we mentioned?
Yeah, affecting the astrometry.
They also affected the photometry in the earlier DR2 release, creating sort of artificial variations in measured star colors across the sky.
And in EDR3?
Largely gone. That was a major step forward in the photometric quality and uniformity.
That's great news. So the colors are more reliable now. What other checks did they do?
A whole suite. Internal checks, looking for inconsistencies within the Gaia photometry itself.
Okay.
And lots of external comparisons, cross-matching with established ground-based photometric standard star catalogs, like Landolt standards.
Comparing Gaia's measurements to those benchmarks.
Exactly. And also comparing with other large sky surveys like SDSS and Pan-STARRS-1, which measure brightness and color in their own ways.
So checking against different systems.
Right. Plus, comparing the observed distribution of star colors, specifically the BPRP color from Gaia, against predictions from Milky Way models, similar to what was done with GOG for kinematics.
Did they find any remaining photometric issues?
The main area noted was, again, in very crowded fields like the centers of globular clusters.
What happens there?
The sheer density of stars can make it harder to perfectly measure the light from each individual one. So in those inner regions, you can see slight shifts in the measured magnitudes and colors compared to less crowded areas. Still usable, but something to be aware of for detailed cluster studies.
Understood. So wrapping this all up, it's just an incredible amount of painstaking work, isn't it?
It really is. The diversity of tests, the cross-checks, the comparisons to simulations and external data, it demonstrates a massive commitment from the entire Gaia consortium to ensuring the data is as trustworthy as humanly possible.
And that trust is fundamental. All these validations are what allow researchers to use Gaia EDR3 to make discoveries, whether it's predicting those asteroid occultations with pinpoint accuracy or, well, redrawing our map of the Milky Way.
Precisely. That rigorous validation is what turns the raw data stream from the satellite into a reliable, powerful tool for science. It builds the foundation of trust.
So, as we finish this deep dive, maybe a final thought for everyone listening. Think about the sheer complexity here. Validating Gaia, this immense astronomical data set, it's a huge challenge. Does it make you wonder what lessons this kind of effort holds for other areas?
That's a great point.
Yeah.
Fields dealing with big data genomics, climate science, even social sciences face their own hurdles with data integrity and validation.
Could the methods used in astronomy, honed on data sets like Gaia's, offer inspiration or even concrete solutions for ensuring reliability elsewhere? What other fields face these kinds of monumental validation challenges? Something to ponder.
Definitely food for thought.
Thanks for joining us on the deep dive.